Hello everyone, welcome on this e-learning platform of Apex Institute of Physics. In this video we will talk about electric field due to spheres, and two types of spheres that we will be dealing is going to be spherical shell and a solid sphere. And we will be using the Gauss law that we have learned in the previous videos to find out the electric field due to these charged bodies. Here we will be considering these charged bodies to be non-conducting in nature, and conductors will be dealing after certain videos. So these charge distributions are on the bodies which are non-conducting in nature. So let's understand first what the results are going to be, and then we will be proving those results. So let's say this blue colored boundaries are this is indicating a spherical shell which is non-conducting in nature. Its total charge is Q, which is uniformly distributed on the surface, and radius is R. Naturally there are going to be two locations that we need to think about. One is the inside the spherical shell, another is outside the spherical shell. So if we talk about the inside, inside means we are taking a distance from the center which is less than capital R. So that's inside location, and the field in this inside location is going to be E equal to 0 at all the points, and outside of this spherical shell the field has a formula which is given by this. So we are talking about the outside, which means R is greater than capital R. Capital R is the radius of this spherical shell, and field is E is equal to K Q upon R square, and it is in the radial direction. For positive charge it's a radially outward, and for negative charge it is radially inwards. So this is the field because of uniformly charged spherical shell at a different locations. So it covers the inside points, it covers the outside point, and there is another point which is on the surface. So if it is asking about on the surface, then we will claim that on the surface R is going to be capital R, and at this point E is not defined. So you will say E is not defined. So this is the result that we need to remember. We will be proving this result. Before we go to the proof, we can also write the same result in the form of graphical representation. So let's see how the graphical representation is going to be. So the graph between the field, electric field magnitude, and position from the center is represented by this graph from 0 to capital R, which is from center point to the just inside the surface. E remains 0 as per the formula. So the graph runs on the x-axis, and just before R it terminates. Then just after R, that is outside field formula is this. So it starts from this particular value and decreases down and reaches to 0 at infinite location. That means it is 1 upon R square. This field is this value which is just outside, its value comes out to be KQ upon capital R square. So that's a field just outside the spherical shell. So inside the field came out to be 0, outside the field came out to be KQ upon R square, just like a point charge. And on the surface, if we are talking about on the surface, it is discontinuous. Hence we say on the surface the field is not defined. However, sometimes it might be asked that let's say there is a small opening on the surface, and at that opening there exists a point P, and you might be asked find the field at this point P which is at this opening. Now if we talk about the field at this point opening where the material is not existing, so at this small opening we will be writing field at the small opening point P is going to be P, the field just outside plus field just inside divided by 2. That means we take average of the inside field and outside field. We know if we are going just outside, this is the maximum field existing. If we are coming just inside, the field is 0. So field at point P will become equal to K Q upon R square plus 0 divided by 2. Hence the answer becomes K Q upon 2R square. So at any spin hole on the surface of hemispherical shell, the field is going to be KQ upon 2R square. So these are the results we need to remember. Let me summarize once again. The field inside at all point is 0. Field outside at all point is KQ upon R square, where R is the distance from the center, Q is the total charge, and field on the surface is not defined. But if the small opening is made on the surface and field is being asked, then we will apply this formula, which is inside plus outside fields divided by 2. That's the average value of the two. And in the case of this spherical shell, it came out to be KQ upon 2R square. Now let's prove that how we are getting these as a result. That means inside field and outside field. So we will see in the next slide how we are going to prove it. So let's see the proof of this electric field due to uniformly charged spherical shell. So let's say there's a shell which is having a charge Q, radius R, and all the charges on the surface shell. That means inside there is no material available. Now there are two parts that to be proved. So first we are targeting this inside. When we say inside, that means R is less than R. We know to prove this, we are going to use this Gauss law. As per the Gauss law, we need to write E ds is equal to charge enclosed upon epsilon naught. So you will see how much the charge is enclosed in this Gaussian surface. So first of all, we need to take the Gaussian surface, and then we will talk about the charge enclosed is going to be. So since we are at the inside point, so let's take a Gaussian surface of radius R. Since it's a spherical symmetric, so Gaussian surface must be spherical. So let's consider a sphere of a smaller radius, and this closed sphere is behaving like Gaussian surface for us. On this surface we need to perform this integration. Now we know whatever the field is going to be, it's going to be radial, and at any point the ds is going to be radial direction. So that means E and ds will make either 0 angle or 180 degree. So in either case they will be parallel to each other. So if we use that thing, so this left hand side, so it becomes E ds cos 0 with integration, and in the left hand side we'll find the charge inside this Gaussian surface. We'll find the charge inside is going to be 0 divided by epsilon naught. After simplification, this will lead to cos 0 is 1, E being uniform can be taken outside, so it's coming E integration ds equal to 0. Now we can think of this integration ds is going to be the total surface area, which will be equal to as E into 4 pi r square equal to 0. Now if we see this expression from here, we can have a conclusion that 4 pi r square is non-zero, hence E must be 0. That means E is 0 at all the points inside the this spherical shell. So that becomes one of the result that we have already listed. So that's proof for inside point. Similarly, we can have a proof for outside point. So let's say outside we are proving it, so R has to be greater than capital R. For this case we need to take a Gaussian surface lying outside. So this is, let's say, charge spherical shell, and we are interested at a point which is R distance from the center. So at this R distance we will be opting a closed surface which is symmetrical. That means it must be a sphere. So let's say that's a spherical surface. This red color is our Gaussian surface, which is a closed surface. And for this Gaussian surface, we will be performing this Gauss law, which is integration E dot ds is equal to Q enclosed upon epsilon naught. Now if we take any element, surface element on this surface, we will find the field is going to be radially outward if it is positive charge, and this is also going to be have like ds, so ds is also going to be in the radially outward direction, so they will have a zero angle as earlier. Further simplification will lead to integration E ds cos 0. Cos 0 is 1, we know, and the total charge inside is going to be capital Q, hence capital Q upon epsilon naught on the right hand side. After simplification, we will find it's going to be E into integration of the ds as we had earlier, so it becomes 4 pi r square. So this becomes 4 pi r square on the left hand side is equal to Q upon epsilon naught. After simplification, this will be equal to E is equal to 1 upon 4 pi epsilon naught, which is K, into Q upon r square. Hence this is the proof. That means E outside came out to be just like a point charge kq upon r square, where r is the distance from the center. So we have proved the second part as well. So these are the proofs for the results that we have discussed earlier in detail. The next is electric field due to a uniformly charged solid sphere. So let's say that is solid sphere. Solid sphere, that means the charge is spread from 0 radius to capital R radius. Let's say the total charge counting is Q and total radius is R. We are interested to find the electric field because of this in the space, that means inside and outside. So let's understand results first, then we will be having a proof. So results are for inside point. So if we talk about the inside point, that means R is less than capital R, the field comes out to be K Q small r divided by r cube, where small r is the distance from the center. If we talk about the outside point, that means outside the sphere, which is r greater than capital R, then E came out to be just like a point charge kq upon r square. And if somebody talks about on the surface, so that will be either from this formula or this formula. Both formula will be agreeing because at that point it's going to be continuous. So inside and outside and on the surface we can find out using this formula. We can also learn the same result in the form of graphical representation. Graphical representation is as follows. So here is the graph, E on the y-axis, R on the x-axis. So it's inside, it's proportional to r, directly proportional to r, so it starts from 0 here and goes linearly there. So it starts from 0 at the origin and goes linearly up to the surface. Then beyond that surface is 1 upon r square, that means it decreases downside. So the second half part is 1 upon r square and the first half is directly proportional to r. This value is going to be the value for the surface as well as just inside and just outside, because there is a continuity, and this value is going to be when small r becomes capital R. Either you place here in the first part or you place in the second part, both will give the same result. So this will come out to be k q upon r square. So this is the graphical representation and this is the numerical or theoretical values. So we can remember these two as a result. Now let's prove how we are getting these as a field using the Gauss law. So let's see the proof. So the proof, let's start with the inside part first. So in case of inside r is going to be less than capital R. Let's choose a Gaussian surface for that purpose. So from here some smaller distance apart, we will take a spherical surface which is going to be a Gaussian surface. This is our Gaussian surface. On this surface we will perform this Gauss law, which is integration E dot ds, and this integration E dot ds is going to be equal to charge enclosed upon epsilon naught. Now we have done this integration quite number of times. We will say the E and ds will be radially outward, that means they will be parallel, so angle will be 0, so cos 0 will become 1. E being a constant can be taken outside, so this will come as E into 4 pi r square. And here is the charge enclosed, so let's say charge enclosed is Q enclosed upon, so this becomes upon epsilon naught. Now if somehow we can find what the charge enclosed is, so our first part will be done. So let's find out the charge enclosed here. So Q enclosed, we know Q enclosed will be the density into the volume, since it's a uniform. So volume is going to be 4 by 3 pi small r cube. Now we know the density, if it is uniformly charged, total charge is Q and total radius is r. So density of the charge is going to be Q divided by 4 by 3 pi r cube. So that's a 4 by 3 pi r capital R cube. Let's place this rho value over there. So charge enclosed will be Q divided by 4 by 3 pi r cube into 4 by 3 pi small r cube. If we settle these numbers, we will find it's going to be Q upon r cube into small r cube. So the charge enclosed is going to be Q small r cube divided by capital R cube, which will become here as Q small r cube divided by epsilon naught into capital R cube. Now from here, if we see carefully, then small r square will get cancelled out. So this will become equal to Q small r divided by 4 pi epsilon naught into r cube. So this becomes equal to, which can be written as K, so K Q small r divided by r cube. So this is the proof for the inside part, and we have just understood that this is a result for inside part. Similarly, we can also prove for the outside part. So let's say go for the outside. If we are working for outside, that means r is greater than capital R, and for that sake again we will start from the Gauss law and we will make a Gaussian surface at the capital at a certain r distance from the center. So let's say that's r distance. We have understood the symmetrical Gaussian surface is going to be spherical, so let's say this is a spherical surface that we are considering, roughly spherical, and here we will be choosing this this is our Gaussian surface, and we will perform this Gauss law, which is integration E dot ds, and that's going to be equal to Q enclosed upon epsilon naught. Left hand side will be similar integration as we had earlier, so it's going to be E into 4 pi r square in totality, and the total charge that we will be watching as enclosed charge is going to be Q, so hence Q upon epsilon naught. From here we can write E as Q upon 4 pi epsilon naught r square, which we can write E as KQ upon r square, just like a point charge. So this is another proof for the outside charge. So this important result and proof we have done over here. So please revise them and follow it. Thank you everybody for watching. All the best.